All right, everybody, welcome to Math with Grace. All right, for this video, we're going to be going through Geometry, Book 1004, Section 1. Section 1 starts on page 2, and it's all about triangles. And triangles are figures that have the same size and shape, triangles that have the same size and shape are called congruent. So any figure that has the same size and shape as another figure is called a congruent figure. Okay, this is going to become a staple of how we do our proofs and what we do here in geometry. Looking at page 3, it tells us that matching the vertices is called a one-to-one correspondence between the vertices of two triangles, okay? The angles at the vertices that are matched are called corresponding angles. 3 corresponding sides also match. So if we look at our triangles here, it tells us that these are all congruent triangles, even though they're facing different ways and one's standing up and the others are on their side. But they're congruent in the fact that AB is the same as GH, which is the same as FE. Okay, those are all equal sides. They're corresponding sides, right? BC corresponds with FD, which corresponds with HI, all right? And CA corresponds with ED, which corresponds with GI. Now, to be able to tell which sides correspond with each other, we need to match up our vertices. And here for model 1, they tell us that A matches E. Now I made a rough cutout of this triangle ABC, right? And to show you that A matches with E, if you flip it over, see how it fits on there perfectly? Well, A is still here, all right? It's just on the back side, see? A, all right? So if we transcribe here and write our letters, our vertices on here both ways. So we can see here that A, if we just flip this triangle over, matches with E, right? They're corresponding triangles, so their parts match. Sometimes when we're working through some of this homework, it might be beneficial for you to trace and then cut out the shape so that you can turn it and twist it in the different ways that you need to. Now, they've got this written here in 2 different models, but I'm just going to keep going. If we move this shape over here like this, we can see that G also corresponds with A and E, okay, throughout these triangles. All right, if we go back to our original triangle and we look at B, it says that B and F are corresponding vertices, and we can flip our triangle over and see that that's true, right? B and F correspond. Now, if we turn our triangle again and line it up here with this one, we can also see that H corresponds with those 2, right? All 3 of those are the same. And finally, if we look at C, which is over here, we'd flip our triangle over, we'll see that C matches D. All right, so C corresponds with D, and if we turn our shape, we'll see that it also corresponds with I. All right, from that, that's how we can get to our corresponding sides. Now, sometimes we know sides correspond just because we know their length, okay? Remember, corresponding sides are equal. They're a one-to-one correspondence when they're equal. And here are your definitions right here. A one-to-one correspondence is a situation when each member of a set, such as angles of a triangle, can be paired with one and only one member of another set, another triangle, okay? Corresponding angles are angles paired with one another in a one-to-one correspondence, okay? So we showed how all of our vertices here corresponded in a one-to-one ratio. And then corresponding sides, we're showing that the sides as well matched up, okay? If a one-to-one correspondence of all 6 parts, vertices, angles, and sides, all of those parts correspond, that leads to one triangle fitting over another exactly, like we did with our shape here, right? I cut it out and I fit it over exactly. Then the triangles are said to be congruent. And the symbol for that is this. It's an equal sign with a squiggly mark over it. Now, when we write congruent triangles, we need to make sure that we're matching up the vertices that are congruent. So when we write triangle ABC is congruent to, let's do this one here, we have to list them in the exact same order of congruency. So which vertice, I'm sorry, was congruent to A? Oops. It was G, right? Which one was congruent to B? That was H. And which one was congruent to C? That was I. So we have to write them in the order in which these congruent pairs match up. Okay? If we switch these orders around, then we no longer have congruent triangles. All right, let's turn the page. So here's another definition, and it more emphasizes what I just talked about, okay? You can write the name of this triangle in any order in which you like, but when you're calling it congruent to another triangle, you need to make sure that you write the other triangle's name in the congruent order as you write the first one. So they wrote ABC here. So is congruent to, you have to write RST because those are the congruent parts to ABC. All right. If you wrote it BCA, then you can write STR. And if you wrote CAB, then you have to write TRS. Okay, the congruent parts have to be in the same order as the first triangle that you named. All right, that's very, very important. And I've talked about this a little bit before. When we mark our diagrams, we mark our illustrations, we want to mark things to show that they're equal. All right, here in this model, they've shown that XY and NM correspond. Now, XY corresponds with MN. We want to make sure we say those. Let me see, does my triangle fit in this one? No. We want to make sure we say those in the correct order. X corresponds with M, right? Y with N, and obviously G with G, because it is that one part. So when we say that XY as a segment is corresponding or congruent to this here, we have to put it again in the same order. And my M corresponds with X, so it has to come first, then the N. Okay, so XY corresponds with MN. YG corresponds with NG. XG corresponds with MG. Okay, you see that we have to match them all together. Looking here at the top of page 5, now they've marked our angles that are equal so that we can say that angle Y is congruent with angle N. G, because these are what kind of angles? These are vertical angles, right? They, of course, are equal. And then X and M are equal. So they've marked each in a different way to show which is equal to which. Now let's go through a couple of definitions and then we'll do a bunch of problems together. Definition here is called an included angle. And it's an angle formed by two sides of a triangle. So if we're talking about this side and this side, the included angle is the angle that is made by the two sides where they come together. It would be this angle. Okay, if we're talking about side AB and side CB, then the included angle would be angle B, because that's the angle created by those two sides. Okay, so the included angle is always the angle created where those two sides come together. Okay, it's included in those sides. Now, an included side is the side of a triangle that's formed by two angles. So if we're talking about angle A and angle C, they share one side in common. What side is that? Well, that's side AC, right? So that is the included side. If we're talking about angle A and angle B, then the included side would be side AB. That's the side that they share. Okay, so that's our definition of included sides. Let's take a look at some of these homework problems. All right, taking a look at page 6, we're going to do some of these problems together. And it tells us to complete the correspondence so that a congruence can be established. Remember, I said establishing congruent triangles is going to be a huge part of our geometry going forward. So it's something we need to become familiar with. So they want us to complete the correspondence. So they're asking us, say for number 1, what does A correspond with this other triangle? Okay, we've got a set here and we have a set here. If we took triangle ABC and we flipped it, like I said, if you need to cut it out so that you can handle it in your hand and see it visually, that's fine. But if we flip this triangle over, it would sit directly on top of this one here. So what angle corresponds or would match up with angle A? Well, that would be angle S, right? Angle S would correspond perfectly with angle A if we just flipped it over. All right, what about B? Which angle would correspond with angle B? Again, we'd have to flip our first triangle over, but it would be angle R. And if S and R are spoken for, then we know that angle C must correspond with angle T. All right, let's take a look at this drawing. This one's slightly different, and let me see if I can make a diagram here. Hold on a second. All right, so I've made a copy. Like I said, I do this quite a bit, so if it works for you, then do it too. I made a copy of EDO. All right, we want to figure out what corresponds with E. Now I need to mark the other side because I forgot to do that one. That's E. This is D. So this must be O. All right, so here's my original triangle, right? Which angle or which vertex here corresponds with E? Well, if I take this directly, all I had to do was twist it around. So it's like a twist of the original triangle. And I see that R corresponds with E, right? Now, what about angle D? Well, angle D, if my shape was, there we go, corresponds with K. They're not always going to line up just perfectly. Sometimes it's twisted or flipped around. So that's why I'm saying sometimes it's very nice just to trace it out, and just cut a small copy of one of the triangles so that you can twist it and manipulate it how you need to. And then O, of course, corresponds with O because they're vertical angles, all right? They correspond to each other because that's what exists there. All right, let's take a look at the next set. All right, so for problems 7 through 15, we've got, again, 2 different sets of shapes, but this time they want us to write true and false on the congruentness of these triangles. Now, I've made one example triangle of each of these shapes, and so I'm going to go from there. So they want to know if triangle ROB is congruent to triangle PTA. All right, well, we have to see then which vertices go together. All right, so I'm going to take my shape over here and I'm going to try to get it to fit. It's not going to fit that way, so let me flip it over. Ah, here we go. Okay, so is triangle ROB, now just because I flipped it over, it's the same triangle, congruent with PTA? It is, right? Because those are the corresponding sides are lined up in that description. So yes, it is true that those are congruent. Is triangle ROB congruent to triangle PAT? It's not, right? Because we said ROB. Remember, when we write congruency, we have to write them corresponding. They have to match. And PAT does not match because P matches R, true, but O and A do not match. B and T do not correspond. So this is a false. What about RBO and PTA? again, this is a false, right? Because even though R and P correspond, B and T do not correspond, and neither do O and A. So this, again, is a false. Okay, what about triangle OBR and triangle APT? Now, right off the bat, we can see that O and A do not correspond, right? Here's my O, it corresponds with T. Here's my A, it corresponds with B. So first, the correspondent we try to make does not work. This is a false. All right, now here at the bottom, it's switching over to this other set of triangles. So let's take a look at those. We've got triangle DEF, well, yeah, DEF. They want to know if it corresponds with WXY. Well, let's see here. Let's move my DEF. That's not going to work. Let me flip this tiny thing over. All right, there's how it corresponds, right? So does DEF correspond with WXY? No, right? Because right off the bat, we know that D and W are not corresponding vertices. So this is a false. What about DFE and YWX? So now we have our D and our Y together, good. Our F and our W together, good. And our E and our X, all of those vertices are corresponding. This one is a true. Those are congruent triangles, all right? What about the next one? FED, does it correspond, is it a congruent triangle with WXY? Well, again, my F and W correspond, my E and X correspond, my D and Y correspond. So these are congruent triangles written like that. That is true. Next one is, oh, we're back over here. Does PAT correspond with WXY? Well, this shape here is the same as this, as PAT, and absolutely not, right? They are not the same shape and size, so that is false. What about ROB? We'll use the original here, ROB. Does it correspond with DEF? No, right? Because they aren't the same shape and size. So that too is false. Remember, when we're talking about congruent triangles, we're talking about parts corresponding or being equal to each other, that the size and shape fit over each other perfectly, which is why we can draw up these different shapes, cut them out, and move them around to help us see what it is we're looking for. Now, eventually, you should get practiced enough that maybe you'll just be able to see it without having to draw these out. But as we're getting started, let's just make whatever we can as easy as we can and use this little hint to help us through. All right? Good job. All that leads us to page 8, which is talking about proving triangles congruent. And it reads, suppose you take two identical sets of 3 sticks. Okay, so there's an identical stick in each pile, and then you put them together. We connect the 3 sticks in each set at their endpoints, and we've got 2 congruent triangles. However we put those sticks together, the 2 triangles formed will always be the same size and shape. The 2 triangles will be congruent because each one of their 3 sides was equal to the triangle on the other side. And that gives us the following postulates. Okay, so here we go again with our postulates. Remember, these are all on our postulates and theorems pages, and you can use those on your quizzes and tests. Okay, they're very helpful. Postulate 11, if 3 sides of one triangle, so this is what the example we just talked about, are equal to 3 sides of another triangle. Let me see if I can fit this all on the screen here. Close enough. Then the triangles are congruent. And so when we write this as our proof, as our reasoning, when we're doing a proof, we just call it SSS, and that stands for side, side, side. Okay, easy, right? We don't have to write all of this out. We just write SSS. That tells us that all of our sides are equal to all the sides of the other triangle, and that's our reason in our proof. The next postulate says, if two sides and the included angle, now remember, the included angle here between these two sides would be this angle, the angle formed when those two sides come together, all right? So if two sides and an included angle are equal to two sides and the included angle of another triangle, then the triangles are congruent. This is called the side angle side. And please make sure you understand that we count them in order. Side, angle, side. Okay, if we were walking around this triangle, that's what we would come to, right? Side, angle, side. Don't get this confused and write side, side, angle, or the dreaded angle, side, side. Okay, none of that in my class. All right, so we have to make sure we put them in the right order. Side, angle, side. If you were walking around, that's how you would come upon them. Side, angle, side. All right. Postulate 13 is if two angles and the included side of one triangle are equal to two angles and the included side of another triangle, then the triangles are congruent. So again, we've got this here. Okay. This time we have this angle and this angle. Now remember, we also have a second triangle. And then this side, the side that they share. So this is angle, side, angle. If you were walking around, again, you'd come to the angle, then the side, then the angle. It's important that you put, when you write these down, that you're writing them in the proper order. This is angle, side, angle. The last thing on this page is a theorem. Okay, bottom of page 9. And it's theorem 4.1, and it tells us if two angles and a non-included side of one triangle are equal to the corresponding parts of another, then the triangles are congruent. So that tells us this. And I'm not going to be able to draw congruent triangles just on the fly here. So, you know, take it with a grain of salt. But if we have two angles, so say this angle matches this one, and this one matches this one, okay, and a non-included side, so let's say this side equals this side, okay, it's not included, right? Included side would be here and here. This is a not included side. But if we can prove that the two angles of a triangle match two angles of another triangle and this non-included side, then we have angle, angle, side. Okay, again, as we're walking around, angle, angle, side. Okay, AAS, angle, angle, side. All right, that's theorem 4.1. Turning to page 10, there's an important note here in the middle. Now, it has a proof that shows you why that theorem is true. You can feel free to read through it. Reading through these will help you to understand how proofs are set up and possibly help you with your proofs as you do them. But here it says we have 4 ways now that we can show that two triangles are congruent. The side, 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 angle, angle, and angle, angle, side. Okay, remember these two are the included, and you can tell that because here the angle is included, right? Because it's in between the two sides. And here the side is included because it's in between the two angles. For this one, it's a non-included side. See how it's not in between? It's on the outside of the two angles, all right? But here are 2 other statements that we need to know do not work, okay? These are no-nos. And the first one is angle, 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 all right? While angles, having all of their angles similar or equal is great for showing similarity, which is something we'll deal with later. This, as you can see by this drawing, the size of the triangles could be different. And remember, when we're talking about congruency, we want their size, their shape and size to be exactly the same. So here, even though their angles are all the same, their shape and size, their size is not the same. So we cannot use that as a proof for congruency. The other one is this side-side angle. So here we have 2 sides of a triangle equal and 1 angle of a triangle equal. But as you can see from this drawing, their size and shape is not equal. All right? So side-side angle is not a proof we can use. No, no, no. All right? Here's another note in the center of page 11, and it reads, remember that when you are asked to write a postulate or a theorem, you should write the statement or its abbreviation. So you can use that SSS or SAS from over here, or ASA or AAS. Okay, that's what they want you to write, rather than writing out the number of the theorem, because the number of the theorem and postulate doesn't always translate. So, but if you talk to someone else taking geometry, they will understand the side postulate or the side angle side. Okay, they will understand that. They won't understand, oh, how are you doing with postulate 4.2? They'll be like, what are you talking about? All right. So that being said, let's take a look at these problems on the bottom of page 11. I'm going to be marking up this drawing quite a bit and erasing it, but it'll be useful as we move forward. So these questions are asking us to write the abbreviation of the postulate or theorem that supports the conclusion that WAS is congruent to NOT. Now, if it helps you, they've already given you your congruent vertices. So if it helps you, perhaps you can mark them as congruent in whatever way best suits you. Okay. Now I know that W and N are corresponding vertices. O and A, S and T, they're each corresponding vertices. So with that being said, let's go ahead with 34. It tells us that A is equal to O, that WA, so that's this, and I'm just going to mark them as I go, is equal to NO, and that AS, which is this bottom one, is equal to OT. Okay, so now that we've got it marked, what postulate or theorem can support the fact that these are congruent triangles? Well, remember, as we're walking around, we want to label it. So as we're walking, we come to a side, angle, side. So that is what we're going to write, the SAS one, okay? That is what we write for number 34. Now I'm going to erase all my markings because it's going to give me a different set for this next problem. I'm not going to erase my vertices markings that I made because that's not going to change. They don't want to change the order of our triangle. They just want us to show which postulate or theorem we would use. So for the next one, it asks us that tells us that WA, okay, is equal to NO. AS, which is down here, is equal to OT. Remember, we have to write them in the order that corresponds. A corresponds with O, S corresponds with T. So we have to write them that way. You can't write AS is equal to TO. It does not work that way. We've got to write them in corresponding order, all right? And then the last part of this problem was that SW, the third one, is equal to TN, all right? So what postulate or theorem can we use for this one? Well, as we walk around, what do we have? We have side, 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 right? So it's our side, side, side postulate. And I'm using my big eraser here because I don't want to burn up my pencil. And I do a lot of erasing, so I keep a lot of erasers around. Taking a look at number 36, let's mark what they've given us here. They've given us that angle A is equal to angle O. Angle W is equal to angle N. And SW, which is here, is equal to TN, which is here. All right, well, remember, we want to walk around this triangle and see what we have. So we have angle, angle, side. Okay, we don't have side, angle, angle. I know you could walk around that way and get it, but the main proof or our postulate that we're dealing with, although this is a proof, is angle, angle, side. So that's how we list it, angle, angle, side. All right, each one of these is just their 3 letters for what we have available to us. All right, get that erased. Let's take a look at 37. 37 is WS equal to NT. Okay, remember, they put them in correct order. W corresponds with N, S corresponds with T. That's very important. AS is equal to OT, and angle S is equal to angle T. Okay, so if we're walking around this triangle, what do we have? Well, we have side, angle, side. Side, angle, side. We've got the SAS again. If we look at problem 38, it says WA equal to NO, WS equal to NT, and angle W equal to angle N. All right, so again, we're going to walk around. What do we have? We have side, angle, side. So that's how we would prove that these two triangles are congruent. Let's erase and start again. 39 gives us that angle W is equal to angle N. Angle S is equal to angle T. And WS is equal to NT. All right, walking around, what do we have here? We've got two angles and an included side, so we have angle, side, angle. Angle, side, angle, right? These are what we're going to list in our reasons when we're doing our proof. We've got our statement side and our reason side. These are going to be our reasons once we've proven this far. All right, let's do one last one. All right, 140. Angle W is equal to angle N. Angle S is equal to angle T. And WA is equal to NO. All right, so again, if we're walking around our triangle, what do we have? Well, we have an angle, angle, side. Okay, even if it was this angle instead, it would be the same. But it's angle, angle, side. So we write angle, angle, side. These are all the different ways that we could show that these two triangles are congruent. Okay. Now, that gives us hope because it isn't just one way to show that a triangle is congruent. When we're doing our proof, we have a lot of options, right? We've got a lot of different things that we could show equal and then relate those back to the triangles being congruent, right? So that is the bulk of there. Now I'd like to do a proof together. So we're going to do proof 144 on page 13. And I've drawn it up on my paper here. And let's see, what did I forget? I forgot my proof thing here. Okay, so we've got our statement and our reason. All right, we've been given the fact that CM is perpendicular to AB and that angle 3 and angle 4 are equal. So right away, I'm going to mark angle 3 and angle 4 as being equal. Okay, and of course, we know that that's going to be our first statement, that CM is perpendicular to AB and angle 3 is equal to angle 4. And why is that our statement? What do we have information that tells us we can say that? Well, that was our given information, right? That's how we know that that is true. Okay, now what are we trying to get? Well, we're trying to get these triangles to be equal, right? We are not equal, congruent, but that means that they're equal. And we can do that in several ways, right? We just learned side, 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 angle, side, angle, side, angle. We've got many options, angle, angle, side. So let's look at our shape here real quick and see what we know. Well, if we folded this in half on line CM, because they share CM, right? If we folded it in half there, well, that would be a pretty good matchup, right? We would have our parts matched up together. So we know that C is corresponding vertices with itself because both triangles share C. And we know then that A and B correspond, right? Because if we fold that in half, they would correspond. They would be touching and correspond to each other. And then we know M, again, is corresponding with itself, since both triangles have that point in common, that vertices. So M corresponds with itself. That being said, now we need to figure out what we've got. Well, first we've got two angles equal, and then they've given us this hint and they've labeled these other two angles. Remember I told you right here in the beginning, they're going to give you hints by telling you where to go. So they want us to show that angle 1 and 2 are equal. Well, from our given information, can we do that? This is the information that corresponds to angle 1 and angle 2. And what do we know about perpendicular lines? What do they create? Right, they create right angles. So for number 2, we can say that the measure of angle 1 equals the measure of angle 2 because perpendicular lines make equal right angles. Now I kind of combine two things, right? Because perpendicular lines make right angles and all right angles are equal. Okay? I combine two things together and that's okay in this instance because they're both relating to these right angles. Perpendicular lines make equal right angles. Okay, this line came down perpendicular here. It created two equal right angles. Okay? All right, so now I've shown that they're equal. I've marked it on my map with the little box. What else do we need? Well, we have an angle and an angle. If we could get this included side, that would be great. But what do we know about CM? Well, both triangles use CM. It's only one line. So of course, it's equal for both triangles. And here's how we write that. All right, this is number 3. We can write that CM, the segment, is equal to CM, the segment, because reflexive is what that's called. This is why I wanted to do this one. If ever we use the same side or the same angle for different triangles, we can call that side or that angle equal to itself because it's reflexive. Okay, if we look at it, CAM is congruent to CBM. They share this side, so it has to be the same length because it's only one side. It's called the reflexive property. CM is equal to CM. They share it, and that's a reflexive, okay, is the reason for that. So now we have, and I always usually mark reflexive sides with 3 marks because I want to make sure I know what I'm talking about, okay, or what I'm looking at. So now if we're walking around this triangle, we have angle, side, angle, right? So we can say in step 4 that triangle AMC is congruent to triangle BMC. Remember, we have to write them with their corresponding parts. A corresponds to B, M to M, and C to C, okay? And why can we say that? Well, what did we have when we walked around? We had angle, side, angle. Angle, side, angle. All right, so there's our proof all done up for you for number 144. Now, turning to page 14, we're going to talk all about right triangles. And here's the basic design of a right triangle. Okay, here's the right angle. The hypotenuse is always opposite the right angle. Okay, it's always across from the right angle. Here's our hypotenuse. The other 2 parts of the triangle are called the legs. Okay, they don't have a specific name right now. They're just called the legs. So here's the beginning of our solving right triangles congruent, and that's theorem 4.2. It tells us if 2 legs of one right triangle are equal to 2 legs of another right triangle, so that's saying that XY is equal to MN, right? And YZ is equal to NO. So now we have 2 legs of one right triangle equal to 2 legs of another right triangle. Then the 2 right triangles are congruent. And this is called our leg-leg theorem. This time we don't have to include this right triangle. We don't have to include this 90-degree angle. Technically, right, we have angle, side, angle. But when we're talking about right triangles, we don't talk about the right angle at all. Just the fact that we have right triangles is enough for us to say leg, leg. Okay? Continuing on that page at the very bottom is postulate 14. And it tells us if the hypotenuse and a leg of one right triangle are equal to the hypotenuse and leg of another right triangle, then they're congruent. So let's draw a couple of right triangles here. Okay, so if our hypotenuse is equal and one of our legs is equal, then they're congruent triangles. And that is the hypotenuse leg postulate, or HL. Continuing on page 15, we've got our next theorem, 4.3. And it tells us if the hypotenuse and an acute angle of one right triangle, so we've got an hypotenuse and one of the acute angles. Remember, when we're talking about right triangles, the other two angles are both acute. They're smaller than 90 degrees. They can't be larger than that. So if we have the hypotenuse and one of the other angles equal, remember, we're not talking about the 90-degree angle, to that of another, then these are congruent triangles. That's called the hypotenuse acute angle theorems, or the HA, the HA. All right, that's one of my favorites, the HA. All right, now I didn't mark what they had here, so don't go off of what's given here. I was just talking and marking at the same time. And our other theorem here at the bottom of page 15 is our law. All right, so we had the LL over here, we had the HL, we had the HA, and now we have the law. All right, so thinking about what we've talked about so far, what do you think the law pertains to? Well, if a leg of an acute angle, the leg and an acute angle are equal to that of another leg and acute angle of a different right triangle, then they are congruent. So we have two right triangles, we have one leg of each equal, we have one acute angle of each equal, corresponding parts. We can use the law theorem to show that they are congruent. Leg, angle. All right, so those are our setups here for our right triangles. Now I'd like to go through a few proofs with you before we finish up this section. And so I'd like to start with proof 1.45. 1.45, we're giving this quadrilateral, right? And they've sliced it in half with a diagonal. They've given us the information that DC is parallel to AB and that AD is parallel to BC. So now we know that not only is this a quadrilateral, but it's a parallelogram, right? Because opposite sides are parallel in a parallelogram. They want us to prove that triangle ACD is congruent to triangle CAB. Now, marking our vertices, our congruent vertices, is going to be very hard for this one, our corresponding vertices. It's going to be very difficult just because they kind of overlap each other. If we took this shape and folded it in half on line AC, would it fold to be even? It wouldn't, right? Here, I just folded it in half. I cut this out before we started. It's not going to be even. So this isn't a shape that we can just fold in half and have them match up. So we need to figure out, well, what does match? Well, if I take my shape that I cut out and I move it around, we can see that it corresponds in this way, just like they wrote here. A corresponds with C, right? C here corresponds with A, and D here corresponds with B, right? So if we follow around the different parts of this, A corresponds with C corresponds with A, and D corresponds with B. But we have to turn this around. So here's how it was. We've got to flip it upside down and line it up like that. So I'm going to leave that sitting there kind of anyway for now as we work through this proof. And I'll move it out of the way if we need to. But let's get set up here. So we have our statement and then we have our reasons, right? Reasons why our statements are true. Always and forever, our first statement is what? It's our given information, right? We know that DC is parallel to AB and that AD is parallel to BC. That is our first bit of given information, and that's our reason. Why is this true? Because it was given to us as being true. Done. Right, now we've done a lot with, I'm going to move this out of the way for right now. We've done a lot with parallel lines, right? in the book before this, we did a lot with parallel lines. We learned the different information that parallel lines can give us. So we are actually going to put 2 bits of information on this next line because they have the same reason. And those 2 bits of information have to do with the angles that they have listed here. And I'm just kind of extending these to show their parallelousness. All right. I'm going to extend this over here. I'm not going to mark that on my line because I'm not actually on my proof because I'm not making auxiliary lines. I'm just visualizing it differently. So looking at it like that, I'm going to grab my ruler. DC is parallel to AB. So this line here is a transversal line, right? It transverses across DC and AB. When it does that, what does it create? Well, it creates alternate interior angles, right? And that would be 3 and 2. Okay, do you see how it cuts through here? And it creates these alternate interior angles. All right, they're on alternate sides of our transversal, and they're inside between our 2 lines that are there. So we can say that angle 2 is equal to angle 3 because if we have parallel lines, then alternate interior angles are equal. Okay, that's our abbreviated thing. Now remember, I said I was going to write 2 things on this line because technically there's another set of alternate interior angles. But to see them, we've got to kind of turn our page. At least I do. And we have that AD is parallel to CB. So again, we have this transversal that is our diagonal of our quadrilateral, right? But it also makes alternate interior angles in regard to AD and BC, and those are angle 1 and angle 4. So turning my page back around, I see that I have angle 1 equal to angle 4, and I can put that on the same line as this one because they are equal for the same reason. Now it's 2 sets of information, but they have the same reason. So just to save space, we're putting them on the same line. Okay, that's a trick that we can use as we go forward. Sometimes we're not going to notice it. And honestly, if you need to add a line or 2 lines to your proof, this one shows that we should have it done in 4 steps. If you need 5 steps or 6 steps to solve a proof, please don't get flustered. Take that extra step and solve it. If you can figure out a way to solve it in 3 steps, it's kind of like name that tune. I can solve that in 3 steps. Then do that. Okay, but it's got to work. It's got to be correct. It has to work. I'm going to read them all individually, but if you need more lines, make more lines. But for this case, we're just going to put these 2 bits of information on the same line because they have the same reason. Okay, here for angle 1 and angle 4, it was the fact that AD is parallel to BC, right? But for angle 2 and 3, it was AB being parallel to DC. All right, this parallelogram gives us lots of good information in that way. Now, we have 2 sets of angles equal to 2 sets of angles of a different triangle. So what do we need to finish this off? We have angle in some form. What's the easiest way for us to prove that these are congruent triangles? This is what we're looking for here. Well, they share a side again, just like one we did previously, right? They share a side, but the problem with them sharing this side is that they don't share it in the same order as the last one that we did. Because here, remember, this is I cut it out to look like that one. I'm going to turn it around. Here, C and A correspond, and A and C correspond. So when we write this one, it's a little bit different, and we have to be careful that we put our corresponding points together. Here, we have to say that AC, which is this line here, is equal to CA, okay? This line here, AC, is equal to CA. Okay, they're opposite. When we put them together, yes, they share the same line, but it doesn't correspond. Remember, we want our corresponding parts together. So if we're taking AC of this bottom part of the triangle, it corresponds with CA from that top part of the triangle. You see that? They're kind of twisted here. This is how we have to write them because this is how it corresponds. Now, it's still a reflexive segment because it's the same thing. AC is exactly the same as CA. They're still the exact same line, but we've got to make sure our parts correspond. We have to write them in the order in which they correspond, and this is the order in which they correspond. AC corresponds with CA. Okay, it's very important. That's why I said if you need to cut out a drawing like I did, then by all means do so. All right, so I like to mark my reflexives with 3 lines. And there we go. We're walking around this triangle now, this upper portion. What do we have? We have angle, side, angle. So we can say that triangle ACD is congruent to triangle CAB because of angle, side, angle. That's what we proved. Angle, side, angle. Okay, make sure we're putting them in the right order. And that's proof 45. The next proof that I want to look at is number 60 on page 19. The reason I want to do this one, and let me see what kind of junk I got over here, is because this and these triangles I'm stealing from a different one we just did. But this, I just want to show you. This kind of represents, let's see here, if this was actually equal, but it represents like a triangle's coming off of a piece of paper. Okay, I just want to give you a visual. The drawing is kind of hard to understand, but it kind of represents something like a bent triangle sitting on a piece of paper. That's what I want you to think of when you look at this drawing. All right, so here's our given information that AB is perpendicular to BD, and that AB is also perpendicular to BC. So that tells us that C, B, and D are not collinear, because if they were, then we wouldn't need 2 statements. Okay, but we know that they're perpendicular. It also tells us that AC is equal to AD. So AC is equal to AD. Now, hopefully, since we've got these perpendiculars here, your mind is thinking, oh, perpendiculars tell us we have right angles. Right angles are right triangles, and ooh, we've got a hypotenuse here. So this is the path we need to start moving down. First things first, we have to label all of our given information so that we can move forward. AB is perpendicular to BD. AB is also perpendicular to BC, and I need an extra space. AC is equal to AD. All right. And all this was given information. We know it's true because it was given to us. All right. So what's the next step we want to take? Well, we've got perpendicular lines creating right angles. Okay. Right angles inside of a triangle make a right triangle. So like we did before, we're going to list 2 bits of information on one line. And that is that triangle ABC, and I'm just going to go with what they give us here, and triangle ABD are right triangles. Okay, how can I say that that's true? What proof do I have that that is a true statement? Well, 2 tells us that perpendicular lines make right triangles. Just like they made right angles, they make right triangles when we're dealing with triangles, okay? So perpendicular lines create right triangles, okay? That's number 2. So now we know we have right triangles. And remember our right uses for our right triangles, right? We have the leg, hypotenuse leg, the hypotenuse acute angle, or the leg an acute angle. Now, the fact that ABC and ABD are right angles, while it's true, it doesn't really matter in the sense we don't have to show that to be true. We've already proven that we have right triangles. And remember that none of these proof statements have anything to do with the right angle itself. So right now we've got a hypotenuse. So we know it's either going to be this or this. So which one can we most easily prove is true? It's going to be this one, right? Because we know that they share a side. They share a leg. And what is that leg? It's AB. They share AB, so we can say that AB is equal to AB. Now in this drawing, unlike the very last one that we did, they share them in congruent order. Okay, their side A corresponds with A, B corresponds with B, so we don't have to write it mixed up. They correspond with each other. So we can say that, and what is the reason we can say something is equal to itself? Reflexive, okay? It is a reflexive property. It is equal to itself. Then step 4, it lists, we could do this in 4 steps, and we absolutely can, because now we have a reflexive side. And what do we have? We have the hypotenuses are equal and one of the legs are equal. So we can say triangle ABC is congruent to triangle ABD because of hypotenuse leg. Okay? And that's proof 160. I want to do proof 162 before we finish this video. All right, so the next problem I want to do is problem 162. Now again, this is a super weird shape. I want you to think of it as like it's coming out of the paper like this. So as a triangle, mine doesn't have a back, but technically this shape does have a back. And it's coming out of your paper like this, with R being the point way up here outside of your piece of paper. Okay, every other point, Q, T, and S is part of this plane, but R is up here off the plane somewhere. It's sticking up out of the plane. It's a different point. Okay, so keep that in mind. I'll leave my little shape over here. But it tells us here that RS is perpendicular to ST. So if this continued on, this would be a perpendicular line, even if it doesn't continue, but if that helps you to see it. RS is also perpendicular to SQ, this line that's kind of in the background. It's like a wedge of cheese almost. You know, picture that sitting there like a wedge of cheese, and that's what we're dealing with here, okay? So it's also perpendicular to SQ. And then they give us the fact that STR, this angle, is equal to SQR, which is this angle. So we're dealing with this triangle here, and then this one that's kind of in the background, all right? That's what we're dealing with here. So almost as if I probably didn't cut this out very well. But yeah, I don't know. That's what we're dealing with. Two pieces that come together like this. All right. But of course they come down because they form a triangle, but like this. All right. That's what we're dealing with. Let me see if I can cut out a different shape that's better. All right. So I've cut out another shape here. So think of it like this. We've got two triangles that are corresponding. Okay, we're going to prove that they're congruent triangles, but they're kind of spread apart at the ends. All right, and they share this side RS. Okay, you can see that right from the drawing. They share this side RS. So we're dealing with this triangle out here and this triangle back here. Those are the two triangles that we're dealing with. It just kind of one is tucked behind the other. All right, that's a little bit better of a drawing or a cutout. Anyway, so let's start our proof. We've got our statement and our reasons. Okay, number 1 is always going to be the same. It's our given information that RS is perpendicular to ST, that RS is perpendicular to SQ, and that angle STR is equal to angle SQR. And this is all given information, okay? I'm going to try and, even though they overlap each other, I'm going to try to label my right angles here just so I can see what's going on. Kind of like that, all right? Now, we want to prove that triangle RST is congruent to triangle RSQ. What do they have in common? Right, this R and S. We've got to keep that in mind. That's our game right there, okay? First thing we need to do is show what? Well, we've got perpendicular lines. What does that tell us? If we have perpendicular lines, we have what kind of triangles? We have right triangles, okay? So what is the name of our right triangles? Well, we're going to use the same names they want us to solve for. Triangle RST and triangle RSQ are right triangles. Why can we say that that's true? Because perpendicular lines make right triangles. Okay? Perpendicular lines make right triangles. Just like they make right angles, they make right triangles. Okay? Step 3. We're halfway there. All right? So we have right triangles. We also have an acute angle. So remember our proofs for right triangles. Leg, leg, hypotenuse, acute, leg, acute. Well, which one are we going to use? Well, we have an acute angle, so it's going to be one of these two. Do we want to try to prove these hypotenuses equal, QR and TR? I don't. That would be a lot of work. But they have something in common already. Remember? They share RS. Remember, their backbone is shared. They share RS. So let's just use that. It's easy. Let's always take the easiest step. RS is equal to RS. Oh, I don't know why I did that. RS is equal to RS. Why? Because it is reflexive. Okay, we're going to use the reflexive a lot, so we might as well get comfortable with it. Reflexive. Okay, so what do we have now? Do we have a hypotenuse acute or a leg acute? We don't have the hypotenuse, right? Because that was going to take too long and be too hard. So we can say that triangle RST is congruent to triangle RSQ. For what reason? What proof do we have of that? Well, we have a leg and an acute angle. So we have our law. We have a leg and acute angle equal to each other, and that is our proof that these two triangles are congruent triangles. Okay? That's it for section 1. There's a good chunk of proofs that you still need to work with and some math problems that you can do. If you have questions, you know how to contact me. Other than that, until next time.